Okay guys, this is Unit 9 video, or introduction video. Unit 9 covers chapters 13 and 14. The focus of chapter 13 is all about solids, liquids, and gases and how they interact with each other. And then chapter 14 spends the entire chapter talking about just gases. So there's a definite reason why when we take a look at this unit page, we see gases really big and solids and liquids really small, because we'll spend maybe a day on solids and liquids, and then we'll spend over a week talking about gases and how they work involved with that. Okay, so when you're working with gases, we have some different units or some new stuff we got to kind of talk about to make sure that we understand in terms of when we talk about different terminology. We've talked a lot about mass already. We've talked a lot about volume already in here, but we really haven't dug into this idea of pressure yet. So we want to talk about pressure a little bit today and get ourselves talking with that, and then maybe a little bit about temperature also. So if you take a look at this idea of pressure, okay, when you think of things having pressure, you might think of like bicycle tires or car tires or basketballs or footballs and that kind of stuff. And you may have experienced where you have a flat basketball or a tire because there wasn't enough pressure in there. And that's because you didn't have enough particles, okay? Because to create pressure, you need to have some sort of particles on the inside of those containers that are flying around, usually as a gas, and are pushing on the outside of those containers, or pushing on the walls of those containers. Okay. Now pressure can be created by solids and liquids also. Like that's how hydraulics work. It's a pressure created by the liquid being pushed back and forth through hydraulic lines. But in terms of gases, it's the same idea, but we have these particles hitting or striking the surface of the container. Now when you measure pressure, pressure is measured in force divided by area. Okay. So it's the amount of force you can create divided by the area. Now if you think about that, if you're looking at how much pressure something can generate, if I ask you the question, what part of your body creates the most pressure, you might jump right to your legs, because your legs can generate the most amount of force in your body. Or you might think about your heart, which is the most cardiovascular or has the most endurance in your body. But really when it comes to pressure, it comes down to your jaw. Because even though the muscles in your body aren't the strongest at your jaw, it actually can create the most pressure. Because if you think about it, pressure is force divided by area. Okay? So if we say that pressure is our force over our area, what we're saying is that if you apply a certain amount of force in a small area, okay, so as area would get smaller, imagine the amount of area between the teeth, or the contact points of your teeth of your jaw. It's a very small amount of area. So if your area gets very small, what happens is, even with a weaker force, you can generate more pressure. Okay? It's really no different than the trick of the man laying down on the bed of nails. It's the same idea. You know, if you lay down on one nail, it's going to puncture you and go right through your body. But if you lay down on thousands of nails, you're spreading out the same amount of force over a much larger surface area. So in reality, you can do that. I've actually done that trick before. I don't have the setup myself, but I actually was at a little presentation on it, and at the end of the show, the person let me actually lay down on a bed of nails and kind of see how it worked. It doesn't feel good, but it definitely won't break your skin as long as you know how to get on and off of the nails the proper way. So keep that in mind as we talk about pressure. It's not just about the force, it's also about the area that's involved there. Now, when we measure pressure, we have 3 different units of measure. Okay, and I apologize for that, but the reality is, in our world, we still have 3 working units that we got to work in and out of. And these are all the ones that are SI related. We're not even talking about the ones that are the imperial ones. Now, the first one is atmospheres. This is the newest of all our labels. Atmospheres basically relates back to one atmospheric pressure, or basically the pressure put on us on the atmosphere around us. Okay, so we're relating the thing back to the atmospheric pressure we actually experience. The second is millimeters of mercury. This is the oldest of all of them. You may have heard this as inches of mercury, maybe as a meteorologist talking about it might rain today because the mercury is falling, or they may talk about it's going to be bad weather because we're going to reduce our millimeters of mercury or inches of mercury. That's where that's kind of coming from. Now pascals is probably the most common one that's used. It's also the standard SI unit for pressure. We often use it in kilopascals because pascals are actually a pretty small amount of pressure. Now, it isn't hard to convert between the two. So if we set them both equal to 1 atmosphere, millimeters of mercury is 760 for 1 atmosphere, and kilopascals is 101.325. Now notice how it is kilopascals, not pascals here. Okay. Now you may be wondering, millimeters of mercury, how do you get a distance or a length to measure pressure? It has nothing to do with force or area. Well, the way they did that is they actually created vacuum tubes, and they would set them in tubs of mercury. And what would happen is the outside of the area of the tub of mercury would be open to the air pressure. And inside that vacuum tube, where there was no pressure pushing down, the mercury would get kind of sucked up or pulled up into that tube because there's nothing there to push against it. There's no atmospheric pressure. Well, as the mercury rose up the tube, it also has mass or weight to it, and so gravity would pull it back down. Now, a balancing act between the two things is basically how much air pressure pushed down on this to force it up the tube versus its actual own weight. And because mercury is a fluid at room temperature, but it's also very dense, it was a great element or substance to use for this, because you could get something that's very dense that was still liquid that could move up and down a column. Okay. Now, we don't use it this way anymore because we don't really like to have mercury open to the air. However, what they would do is they would just mark along the column different millimeters or different inches, and however far the mercury went up, they would mark that and say, oh, it's up here at 760 millimeters of mercury. And they said that's about normal atmospheric pressure, okay, or about 30 inches of mercury if you convert that over to inches there, okay. So that's what they kind of get this idea of millimeters of mercury from. Now, how can we increase pressure? Okay, so if you think about it, well, we have force over area, so if we want to increase pressure, we can make the force greater, or we could reduce the surface area. Those are the two ways we can do that. So through this unit, we're going to be talking about increasing and decreasing pressure by changing force. And force has a relationship to mass and acceleration and velocities and speeds, which will have a relationship to temperature. Okay, and then of course area is related to the volume that the substance is contained in. So we'll be talking a lot about the volume of our different substances also in this. Now, if we talk atmospheric pressure, we don't even realize it, but we're constantly under pressure. Okay, and I don't mean like pressure for mom and dad to do well at school, or pressure to get into a good college. I mean legitimate, realistic, real pressure, because the air that we walk through is pushing down on us at all times. Okay, so we don't realize it because we just live in it, and our bodies are designed for that. It's really no different than fish in our waters, because they have bodies that are designed for that. So they don't really notice the pressure unless they go too deep, but they are designed to move around in water that way, just like we are designed to move around through the pressure of the air around us. Okay, so if you can imagine, wherever we stand, we have a column of air pushing down on us at all times, and pushing from the left and right and all over the place, and that's our atmospheric pressure. Okay, if you take basically a 1 meter squared column pushing down on this, it has about a mass of 10 to the 4th kilograms. Okay, and that is going to equal an atmospheric pressure pushing on us. So we always have pressure on us. So keep that in mind as we go through this unit, that there's always external pressure pushing on us. So we need to have internal pressure to maintain volume and that kind of stuff. Okay. Now, if you take a look at pressure, we have two ways to measure it. We have something called a barometer and then a manometer. Okay? Barometers are used to measure atmospheric pressure. Okay, they look like devices like this, and this is an old analog one. They also have digital ones now that change resistance. But the old ones basically would have a tube that was wound up in here, and depending on the pressure, the vacuum chamber, the gases in here would shift, which then would cause the needle to move under pressure. But barometers are all about atmospheric pressure. Manometers are still measuring pressure, but they're trying to measure the pressure inside a container. Okay, so for example, you may have a simple manometer that is just a U-shaped tube. If the pressure on the outside of the container and on the inside of the container are the same, we get a 0. If they're unequal, so if this would go to the inside of the container, we would say that the container is under pressure. If the inside of the container is higher, we would say we'd have a vacuum. And I'll actually show you one of these in class when we come back. Okay. Under the same token, that's kind of how the mercury chambers worked for our millimeters of mercury. Is basically you have a vacuum chamber, atmospheric pressure pushing down, and the pressure due to the weight pushing back, creating that different column of air. Now you may wonder, what is this thing over here? This is actually a picture of my basement, and this is a picture of my attic. In my basement, I have this tube coming out of the concrete that has this little dial on it. This is blue liquid in here. And that runs all the way through my house up to the attic with this fan on it. And this fan runs always, at all times of the day. Okay, it's very quiet. I don't ever hear it. It's above my insulation, so it's just constantly running. Now the reason why I have it is because I want to create negative pressure, or I want the inside of this tube to be a vacuum. Okay, so you notice how the tube runs here, runs down into here. That indicates that I have a vacuum inside this tube compared to the outside, because I want the inside of this tube to be less pressure than the outside or the air around me. What this device does, this is actually called a radon abatement system. So what it's doing is it's constantly pulling air from underneath my house, sucking that air out, creating vacuum from this fan, which is constantly pulling whatever gases are underneath my house. Now the reason why I have this is because when I bought my house, I tested for radon. And Dakota County is notorious for having bad radon problems. So because my house tested positive for radon, I had to put this in, so basically I could get the radon gas up and out of my house so it would not hurt us. Now if you didn't know, radon gas is a carcinogen. It's actually one of the leading causes of lung cancer in our country, right behind smoking. So long-term exposure to radon gas can be very dangerous to us. So I bought a house that has it. Now by putting the system in, I should be safe, but we'll find out in a few years if I get lung cancer, because I don't smoke, so it will be the radon. All right, so that's kind of pressure. Now, if we take the next step, is we need to start talking about kinetic energy and temperature, and this is what we'll lead into in our class tomorrow. Thanks, guys.